How's it going, everyone? For today's video, we are going to learn how to do stoichiometry in chemistry. If you're watching this video, I'm going to assume that you already know what stoichiometry is and you have an idea what molar conversions are. Otherwise, you wouldn't be clicking on this video. So I'm going to try and keep this short, no real intro. I'm just going to dive right in how to do stoichiometry. If you are unsure or unfamiliar with molar conversions, how to convert between mass and moles, I encourage you to click on this link, go to that video, watch that, and that might help you with this process. With that said, let's go ahead and take a look at our first example. Okay, for this first example, we're going to take a look at the decomposition of hydrogen peroxide. That's that stuff in the brown bottle that you get in the first aid section of stores. And that decomposing into water and oxygen gas. This is something you can do in the classroom. That's pretty fun. Take a catalyst, put it into the hydrogen peroxide, and you'll watch all the oxygen leave the water. And it's a fun calculation that you can try and do for a lab setting. Now, we cannot jump from 1,000 grams over to figure out how many grams of water and O2 would be left over. In order to figure out, let's say, how much water would be left over after this is completely reacted all the way through, so there's no hydrogen peroxide left, we would have to first figure out how many moles this is of hydrogen peroxide, figure out how many moles of water would be produced as a result of this chemical reaction, and then we can take that number of moles of water that gets produced to figure out how many grams of water would be left over. So the first thing we got to do, and I'm going to use a different color so we get some contrast in this. We're starting off with 1,000 grams of H2O2. To figure out how many moles of hydrogen peroxide that is, we need to know the molar mass of hydrogen peroxide, which is about 34.01. We multiply this by a unit conversion factor that includes that, putting the 1 mole on top and the molar mass of hydrogen peroxide on the bottom. When you do that, you go 1,000 times 1, that gets you a unit conversion factor of 1,000 over 34, so then you would just divide 1,000 by 34. So 1,000 divided by 34.01, that gets us to about 29.4 moles of H2O2. So we would put that right here, 29.4 moles of H2O2. This is a nice new marker. Okay, next thing we got to do if we want to figure out how many grams of water is we need to figure out now how many moles of water would get produced if we reacted this many moles of hydrogen peroxide as a part of this chemical reaction. And to do that, we need to use these numbers up here. What these numbers represent is just the ratio of molecules of hydrogen peroxide that would produce water molecules. So for every 2 hydrogen peroxide molecules that we have, 2 molecules of water would end up getting produced for every 1 molecule of oxygen gas would get produced as a result of this. So we would use these ratios to figure out the ratio of this. This is going to be a 2 to 2 to 1 ratio, meaning that this number of moles here is going to be the same as this, because the number of molecules here is the same as that. And this is going to be about half as much as that, because this would be a 1 here. Since there is 1 molecule produced here for every 2 here, half as much, so we would just cut that in half if we were trying to figure out oxygen. So for here, since this is a 2 to 2 ratio, I'll just show that really quick. 29.4 moles of H2O2 times, we want 2 moles of H2O over 2 moles of H2O2. That would get us, well, that's the same thing as 1 over 1 moles of H2 would cancel. 29.4 moles of H2O. We just put that right there. To convert from here to here, that is the number of grams of water that would be left over compared to the moles of water that gets produced. We would just do the same thing that we did here, only flipped. So we'll put our 29.4 moles of H2O. Multiply that by a unit conversion factor that includes the molar mass of water, which is 18.02 grams for every 1 mole of H2O. And that would come out to 529.79 grams. And we put that up here. Reason we put the molar mass on top is because, because we're trying to figure out grams, and when we do that, we need the molar mass on top instead of the bottom. Okay, we figured out how many grams of water would be left over after this reaction had gone to completion. Let's say now we wanted to figure out how many grams of oxygen would be left over, or we would have lost as a result of this. Let's say we put some manganese dioxide into the hydrogen peroxide, watched it all react all the way to completion. We figured out that this much water is going to be left over. Now we need to figure out how many oxygen gas grams, moles that we lost. So we would start right here in the moles. We cannot go straight from grams to grams. Actually, we can. I'll show how to do that in a moment. But we need to start with the moles here, assuming we didn't know any other information. So for every 29.4 moles of H2O, there is 1 mole of oxygen gas that is produced for every 2 of these. So we put the 1 on top, water on the bottom. So this is going to be half as many moles as the water moles that we begin with. So 29.4 times 0.5 gets you 7 moles of oxygen gas. And then from there, we can figure out how many grams that we lost. And then I'll show, once we know all this information, we can take this information and also figure this out, and we'll do that just to compare for this first example. So we have 14.7 moles of oxygen gas. We would multiply that by the molar mass of O2, which is 32. Per mole, and that gets us about 470. Oops. 0.4. Okay, so here's what this means. If we started off with 1,000 grams of hydrogen peroxide and we reacted that all the way to completion, we should get 529.79 grams of water and 470.4 grams of oxygen gas. Now oxygen, that's a gas obviously, so unless you found a way to contain all of it, that's all going to get tossed up into the atmosphere, out into the air, and you're not going to really have a way of measuring that. So the only way to measure that in lab would be to take the amount of water that you have that is still in your beaker, your Erlenmeyer flask, whatever you're working with, and subtract that from the total amount of hydrogen peroxide that you started with. And that is another way you can go about figuring this out if you knew the masses of other things. So I'll just show that really quick. So we had 1,000 grams of H2O2. We would subtract that by 529.79 grams, adjusting for error, or accepting that there's going to be a little bit of error in this. And that would get you the total number of grams of O2. So 1,000 minus 529 0.21 grams of O2. And look at that. We were pretty darn close. We were off by about 0.2. Those of you that really put an emphasis on significant figures and rounding error, this is just to show the steps here. So I apologize to you significant figure people out there. Let's go ahead and take a look. We're going to do 2 more examples. Okay, another fun chemical reaction that we do in class is the thermite reaction. We start off with 150 grams of thermite. Try and figure out how much aluminum, powdered aluminum, would be needed in order to react with this. I guess that's rust is what that would be. And then from there, we can kind of try and figure out how many grams of iron would end up being produced as a result of this chemical reaction. Move that down just a smidge. There we go. Now, same steps as before. Write this out fully balanced, all the way complete chemical reaction or chemical equation for this chemical reaction. Organize it into each substance and the mass versus the moles. If we knew the number of grams or the mass of what we were starting with here, we can then use this information to figure out the number of moles. And for the sake of this problem, we want to figure out the number of grams of aluminum that we would need to react with this to completion. So we would have to first figure out the number of moles that this is, how many moles of aluminum would be necessary, which it looks like it's going to be a 1-to-2 ratio here, so about twice as much. And then from there, we can figure out how many grams of aluminum we'd have to weigh out. Okay, to go from grams of iron oxide to moles, we need to multiply this by the molar mass of iron oxide, which is, so we'll start 150 grams. Multiply that by the molar mass, or a unit conversion factor that contains the molar mass. This is going to be 1 mole on top over 159.69 grams. And this is going to be the same thing as going 150 divided by that. So we'll do that. 150 divided by 159.69 gets us about 0.94 moles. Once we figure out the number of moles here, we can use this information and this information up here to figure out how many moles of aluminum would be produced. So for every 1 mole of iron oxide, it takes 2 moles of aluminum to react to all that iron oxide to completion. So we would take this information, take the number of moles, 0.94, multiply it by a 2 aluminum to 1 mole of iron oxide ratio, and we would get, well, twice as much. So what's 0.94 times 2 gets us 1.88 moles. Okay, once you figured out the number of moles here, we can then go and figure out the mass of aluminum that would be necessary for this chemical reaction. So to do that, we take the number of moles of aluminum that we would take to go get this reaction to completion, multiply that by another unit conversion factor that would include the molar mass of aluminum, which is 26.98 grams per mole. And that would get us about 50 grams of aluminum. Oh man. So for every 150 grams of iron oxide, it would take about 50 grams of aluminum to react it to completion. Let's take this one step further. Let's say we wanted to figure out how much iron would be produced as a result of this chemical reaction. When you do this, you get a lot of molten iron, and it's kind of cool to look at once the reaction's gone to completion. There's a few ways to go about doing this. One way is just to use this mole. The other way is use this mole amount here. Take a look at the coefficients up here that tell you the ratio of iron atoms that would be produced when these two react together. We have a 1:2 ratio. So if we use this mole, we would have to, again, multiply it by 2. But this is also a 1:1 ratio. So we could just take this and know that for every 1.88 moles of aluminum that we react with iron oxide, iron oxide, we would get the same number of moles of iron. So we could just write 1.88, save ourselves the trouble. And then if we wanted to figure out the mass of iron, we would just take the molar mass, multiply it by that to get that. So let's see here. We got 1.88 moles of iron. The molar mass of iron is 55.85 grams per 1 mole. And if we reacted that amount of iron oxide and aluminum, we would get, or should get, about 104 grams, 105 grams. Yeah. 105 grams of iron. And then with this last bit of information here, say we wanted to figure out about how much aluminum oxide would get lost. This is more of just kind of like an ashy substance after this chemical reaction kind of gets aerosolized, lost to the air. But if you wanted to figure out, you could do it two ways. You could just take this information, add this mass here and this mass here together and subtract that from it. Or you could just keep going your route here. This is a 1:1 ratio here, 1 aluminum oxide for every 1 iron oxide. So we would just take that 0.94 moles, put them here, and then multiply that by the molar mass and figure out that last bit of information. Let's go ahead and look at just one more example. Okay, last example here we'll take a look at is the stoichiometry of the neutralization of hydrochloric acid and sodium hydroxide into water and table salt, sodium chloride. This is something that you can do in a titration. That would involve some molarity calculations, and we'll talk about that in a future video at some point. But for now, we take 40 grams of sodium hydroxide. How many grams of hydrochloric acid would be necessary to neutralize that sodium hydroxide? And obviously that you're not going to really measure hydrochloric acid in grams. That would be in milliliters, but we know the moles here. Actually, let's just find the moles, and well, that'll make this a shorter clip here. How many moles of hydrochloric acid would be necessary to neutralize that sodium hydroxide? Okay, we know the number of grams of sodium hydroxide that we may or may, that we dissolved in some water to do this titration. What we need to do is first convert this to this, and then we can figure out the number of moles that is. So we take 40 grams of sodium hydroxide, multiply it by a unit conversion factor of 1 mole over, it's about 40 grams per mole. And oh smokes, that's about 1 mole. That makes this nice and even, give or take a little bit. It's a little bit more than 1 mole. Okay, once we figured out that, we use the molar conversions here to figure out the ratio here, and everything in this chemical reaction is a 1:1 ratio. So we have 1 mole here. It would just be the same number of moles here. And then from there, we wouldn't try and figure out the mass of hydrochloric acid because hydrochloric acid is in a liquid and it can vary in concentrations. you would figure out first the molarity, use the molarity of what you're working with to figure out how many milliliters that you would need to neutralize that, and you would move on from there. But we'll save that for another video. That's all for today. I hope you guys found this helpful in your chemistry academia. Good luck to you in the future. Thanks for watching. Please like and subscribe if it helped, and I'll catch you all in the next one.